All right, so let's go ahead and chit chat a little bit.
Hey, Bill.
Hey, how are you?
Oh, you up with that?
Review session. So exam 2. "25 questions, 1 bonus. Same format as before, right? I'll give you a zip grade form. Be prepared for that. You can have your model kits, your notes, handwritten, printed out, and you can have a calculator. And nothing that can access the internet, and no book. Same as before, nothing new there. So, with that in mind, it's going to be about mid-chapter 5 all the way to 9.4. So, those are the topics we are going to cover, and I will now open it up to you all for questions.
So what is the mechanism for alkyne being reduced to alkane? I'm very confused about it.
Yeah, so an alkyne being reduced to an alkane, we did not go through the mechanism per se. It's a very complicated mechanism, actually. But basically what you need is you need hydrogen gas, and you need a catalyst like palladium, platinum, or nickel. And that will take you to the alkane. Right, so we actually need 2 moles of hydrogen at least, right? So keep everything balanced for every mole of alkyne. And so palladium will work, or platinum, or nickel. There are others, but those are the common ones that you all need to know about. And basically the way that this works, if you think about the surface of the table being the surface of the palladium catalyst, hydrogen gets absorbed onto the surface. And so if you imagine me drawing a surface here, right, and on that surface, hydrogen gets attached to it. So this is the palladium surface. Hydrogen gets attached to it all over the place. And what happens is that the alkyne, the pi bonds can interact with palladium as well. It forms what's called a complex. And so as the alkyne interacts with the surface of the palladium, the hydrogen and the carbon get close together, and you can get a transfer of a hydrogen atom to a carbon. And then once that happens, it dissociates. But what you have here is you actually have 2 double bonds, right? Just happen to be 2 double bonds, if you want to think of it that way. 2 pi bonds, I should say, right? And so you can reduce the first one, but it will also reduce the second one without stopping. I mean, that's what palladium does. Now you can reduce an alkyne to an alkene and stop there and just add 1 mole of hydrogen, but you have to use a special catalyst. You remember what that is?
Lindlar.
That's Lindlar's catalyst, that's right. Lindlar catalyst. Now we didn't talk about what, but it's a palladium catalyst that's poisoned. And it will reduce the alkyne very quickly, but it actually will stop and not reduce the alkene. Actually, it will probably reduce the alkene if you gave it a long, long time, like years. But it allows you to stop it at the alkene. So you can actually take alkynes and you can make alkanes, and you can take alkynes and you can make alkenes. And the nice thing about this is that alkynes are actually very useful to make a number of other things, right? So for example, you can take an alkyne, if it has a terminal hydrogen on it, and you can remove that hydrogen using a base. And we said that we would use sodium amide, it's what we used in class. and that gives us this. Plus ammonia. This picks up that hydrogen, right? So it's just a simple little reaction where we get the alkyne, and these are good nucleophiles, right? So now we can react that with a good nucleophile, something like, oh, let's just say CH3 iodide, right? Methyl iodide, or iodomethane. And we can do an SN2 reaction that now allows us to make a carbon-carbon bond. And so we can make that carbon-carbon bond now, and now we can take that and hydrogenate it, either to give us an alkane or hydrogenate it to give us an alkene. So that's a possibility. It's a nice thing about alkynes, that terminal hydrogen turns out to be pretty reactive towards base. So we can make carbon-carbon bonds pretty easy. Answer your question or too much?
Yes.
Any questions about that? Hey, come on in. What else you got for me?
How can you determine the stability of, I think it's carbocations, maybe?
Carbocations? Yeah, so carbocation stability. So a carbocation is a carbon atom that is sp2 hybridized. And I'm just going to draw out some different things here. Right, so 3 things attached to the carbon. The p orbital is empty. So overall, if you calculated the formal charge, right, carbon comes in with 4 electrons. It has an electron here, here, and here. So it should have a +1 formal charge, and in fact it does. And so it's got a positive charge. And I'll just put it in the carbocation. Okay, makes sense that it would be there. And so it's a positively charged carbon atom. They're not particularly stable, but they can be formed. They're intermediates. They're intermediates on the way to addition reactions to alkenes, for example, and I'll show you some examples in just a moment. But it turns out that the more R groups you have attached to the carbocation, the more stable it is. So for example, if everything here is a hydrogen, this would be a methyl carbocation. This is not stable at all. And in fact, for all practical purposes, you can't form it. A guy got a Nobel Prize for doing it, but it uses this stuff called magic acid, and it's pretty nasty stuff. And it doesn't, even then, it doesn't live very long. Okay, but it's not very stable. But what we find is that when you add an R group, so let me just use something like methyl. We'll just say methyl is our R group. Okay? And so we got some hydrogens here, hydrogen there, got my p orbital, my positive charge. It turns out that that alkyl group, because it has this bond has electrons in it, and it can help stabilize that carbocation. So this carbocation is not particularly stable, but it is much more stable than the methyl cation. Now if I add another alkyl group, and again I'm just picking on methyl, what you see is that I've got this bond that can donate electrons into here, and I've got this bond, or one of these, doesn't matter which one, also. So I've got 2 groups that can actually help stabilize that carbocation. So what we find is that this is much, much, much more stable than this one. And then we can imagine a scenario where we have a tertiary carbocation where I have 3 groups. And I drew that bad, I'm sorry. Well, now I have 3 groups with these types of electrons that can help stabilize that positive charge. And so that's actually even more stable than that one, all right? So we know that the order of stability is tertiary, more stable than secondary, much, much more stable than primary, much, 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 much more stable than methyl. Okay, so the more substituents we have on that carbocation, the more stable it is. Anything that can delocalize that positive charge will help stabilize it, okay? And so we see examples of this, right? I told you about a cardinal rule of carbocations. And what was that cardinal rule? What was the cardinal rule of carbocations? It's not in your book. Might be in your notes, should be in your notes. What did I tell you that carbocations love to do?
Rearrange.
They love to rearrange. The cardinal rule states, the cardinal rule is my rule, but the cardinal rule states that if a carbocation can rearrange to a more stable carbocation, it will. Okay, so for example, let's say we take and let's say we add water, sulfuric acid, a small amount of sulfuric acid, so a catalytic amount. What reaction are we going to do? The just general reaction, before we think about rearrangements or anything. If I have an alkene and water and sulfuric acid, what's the product I'm going to get? An alcohol. That's exactly right. I'm going to get an alcohol, right? I'm going to get an alcohol. And so I've got to be very careful here about carbocation rearrangements. Actually, this is a bad example. Let me erase this. Let's do it differently. This is a better example. Okay. So the first step in this reaction is for a hydrogen atom to go on one of the carbons of the alkene. Whose rule is that? Markovnikov's rule, that's right. So I've got carbon number 1, which has 2 hydrogens. I've got carbon number 2, which has 1 hydrogen. So which carbon is going to get the proton? Or the hydrogen? Carbon 1 or carbon 2? Carbon 1 or carbon 2? You said it right. Which one?
Is it the least substituted?
It is the least substituted. Another way to word it is the carbon with the most hydrogens, right? So this carbon is going to get the hydrogen, right? Because I've got water and sulfuric acid. I really have H plus around. And HSO4 minus and water, right? And so this is going to react and pick up the proton. And so I end up with this secondary carbocation, right? So this carbon got the hydrogen. I'll just go ahead and draw that in. Let me put CH2 here. And so that way you can see that that carbon really did get the proton. What kind of carbocation is that?
Secondary.
It is. It's a secondary carbocation. Is it the most stable? It is not the most stable. It's okay, but it's not the most stable. But this can rearrange to a more stable carbocation. One of these methyl groups, they're all equivalent. This carbon right here. So anytime you have a carbocation, look at your alpha carbons, the carbons, or the beta carbons, the carbons that are directly attached to the carbocation. And ask yourself, can something move? One of these groups can move. So this CH3 could move here. We call this a rearrangement. And that puts the carbocation here. What kind of carbocation is that? That is tertiary, right? So, since it can move and make a more stable carbocation, will it do it? Absolutely it will, right? So that's the carbocation that you get, and now water can attack that. and I get that alcohol. So it looks like I've added a hydrogen here and an OH over there, instead of adding the H and the OH across the carbon-carbon double bond. But that's because it shifted and it moved, right? So got to keep that in mind. We can have carbocations rearranged. So anytime on the exam that you draw a carbocation, pause and think about it. Can it rearrange to a more stable carbocation? If the answer to that is yes, do it.
So if it's, so there's like a methyl group that's not attached to a beta carbon, can I rearrange then or not?
No. You have to look at these beta carbons. Okay. Are there examples? Yes, but they're pretty rare. And this is what 99% of the time happens. So we're just going to focus on that. That answer your question? I can guarantee you there will be at least a couple of problems that deal with carbocations. And so you have to determine whether or not they will rearrange or not in terms of giving the products. Don't forget your chemistry of alkenes, right? So you should have some flashcards made or whatever to show what you can do to an alkene, right? We can add hydrogen if we have a catalyst and make an alkane. We can add halogens and we can get dihalides. We talked a little bit about that today, didn't we? When we were doing our little demonstration, we talked about that. We can add water across the carbon-carbon double bond, sulfuric acid. We can make alcohols. Now, I'm not giving you all the details of these reactions. But what you need to know when you look at a problem, you go, well, he gave me an alkane, water, and sulfuric acid. You immediately need to know that's going to make an alcohol. Now, that alcohol could be a product of a rearrangement. Not in this case, but it could be. Okay? We learned that there was more than one way to make an alcohol, right? There's the hydroboration oxidation sequence. And we can make alcohols there. In this case, it's the same alcohol, but you need to review the differences that are in the book. It's very important. That's in chapter, that's around 5.6 where it talks about that. Okay. So we learned that we can do a variety of different things too. X here, of course, is chlorine, bromine, for all practical purposes, right? So X equal. We learned today that we can add an oxygen atom across an alkene, didn't we? We learned that we can add an oxygen atom across an alkene. And what did that make?
Oxide.
Yeah, it made an epoxide for us, right? So, and we need a peroxy acid of some sort to do that, right? So we learned that we can add a single oxygen atom across the carbon-carbon double bond. That's kind of cool. Right? So we learned all of these different things that we can do to an alkene. What else you got for me?
So, say you have like just on like the carbon atom, you have an OH group, hydrogen, CH2 and CH3. Which would be a higher priority, CH2 or CH3?
Repeat that, please.
So if you just have like a tetrahedrocarbon that has like an OH group, a CH2, CH3, and a hydrogen, what would be, which would be higher priority?
Okay, so assigning priorities here, right? We always look, so you're looking at this saying that's a chirocarbon, right? And so if you wanted to assign priorities to that, you look at the atoms that's attached to the chirocarbon. I've got oxygen, hydrogen, carbon, and carbon. Can I make a decision? I can make a decision about a couple of things. What can I make a decision about?
Highest priority.
I can make highest priority and lowest priority, right? How do we determine priority? We go by the atomic number, right? So I've got oxygen, hydrogen, carbon, and carbon. Oxygen clearly has the highest atomic number. This is going to be number 1, highest priority. Hydrogen's going to be number 4, lowest priority. Now I've got 2 carbons. So what do I do now? I have to ask myself what's attached to those carbons. What's attached to this carbon? Simply 3 hydrogens. And I always put these in parentheses. What's attached to this carbon? Another carbon, I don't know what it is, I put an R group there, but let's just put carbon, and 2 hydrogens. You always put in parentheses things from highest priority to lowest priority. Okay? Now I look inside the parentheses, I've got carbon and hydrogen. Can I make a decision? Yes. Which one is the highest priority? This one. So this is number 2, this is number 3. So now we know the priorities. If I built the model and I knew that the hydrogen, I can turn it away and then I can look whether it rotates right or to the left, right? Correct? I mean, not right. Correct. So that's how you can determine priorities. What else you got for me? Ask. It's fine.
Acid catalyzed hydration.
Acid catalyzed hydration. Yeah, that was just what we talked about in terms of making alcohols.
Yeah.
That was that mechanism we went through, right? So an alkene will react with water in the presence of acid, like sulfuric acid. And it will make an alcohol because it's adding H and OH across the carbon-carbon double bond. In this case, it didn't matter which hydrogen, where the hydrogen went, because they're the same. They both have the same number of hydrogens on these 2 carbons. They both get the same product. But you have to remember Markovnikov's rule. Markovnikov. We can also do the reverse. I can take the alcohol and I can remove water and get an alkene, right? Instead of adding water, I just use sulfuric acid, and it will do the backward reaction. Okay. So we can take alcohols and convert them into a variety of things. We can also take alcohols, right? What happens if I take an alcohol and I react it with something like HBr? Hydrogen bromide, what do I get? We'll get into some chapter. We get into some chapter 8 stuff there, where we were talking about alcohols and stuff, right? What I'm going to do is I'm going to convert the alcohol into a halogen. Right, so remember, we learned that we can convert alcohols into a lot of different things too, right? So we can take, let's just make a roadmap for that. So let's say I've got a generic alcohol. I'll just pick on cyclohexanol. And I can react it with HX, where X is equal to chlorine, bromine, or iodine, and I can replace the OH with X. So I can go from alcohols to alkyl halides. Right, we talked about that. I can also react an alcohol with PX3, where X is equal to chlorine or bromine. And I can make alkyl halides, it's another reagent, to do the same thing. I can react the alcohol with SOCO2, that's thionyl chloride, and I can make alkyl chlorides. Okay. I can take the alcohol and treat it with sulfuric acid, and I can make the alkene. So we can do a lot with alcohols too. I can do a lot with alkenes, I can do a lot with alcohols. Right?
How to calculate oxidation states?
How to calculate oxidation states. Let's take this molecule. It's called dimethyl carbonate. Now let's suppose I want to know the oxidation state of that carbon. Finding the oxidation state of an atom is exactly the same as doing formal charge, except you don't assume equal sharing. So let's first calculate the formal charge of that carbon. How many electrons does it come in with from the periodic table? 4. I circle it, right? And I see how many it owns. It owns 1, 2, 3, 4. 4 minus 4 is equal to 0. It has a 0 formal charge. But that is not its oxidation state. Its oxidation state is different. It still comes in with 4 electrons. But now we subtract from it those that it really owns. Not formally. We assume in the oxidation state calculation that the more electronegative atom gets all the electrons. What's more electronegative, carbon or oxygen?
Oxygen.
So it's not going to get any of these electrons, right? So just erase them. What's more electronegative, carbon or oxygen? So erase those. What's more electronegative, carbon or oxygen? So erase those. What's more electronegative, carbon or oxygen? So erase those. So how many does it have around it? 0. So it is in the +4 oxidation state. It has a formal charge of 0. It's not charged, but it is highly oxidized. It's in the +4 oxidation state. Okay? So that's how you calculate oxidation state. So let's look at a different example. Something that isn't quite so rote. So let's suppose I have CH, CH3, CH2, CH3, bromine. And I want to know the oxidation state of that carbon. What do? I know it comes in with how many electrons? 4. And I'm going to subtract from it those that I'm going to assign to it. What's more electronegative, hydrogen or carbon? Carbon. So I'm going to...
I found from Wikipedia.
It gets both of those electrons, right? So it gets those 2. What's more electronegative, carbon or carbon? Neither, right? So how many electrons of this bond do I get? Not 0. 1. It gets 1. What's more electronegative, carbon or carbon? So it gets how many of the electrons? 1. What's more electronegative, carbon or bromine? Bromine, yeah. So how many of these electrons does it get? 0. So it's 4 minus 4 equals, it's in the 0 oxidation state. What about a simple molecule like methane? Whoop. How many does it come in with? 4. How many does it now own? What? We know that carbon's more electronegative than hydrogen, right? So it gets all the electrons. So how many electrons would that be? 8. It's in the -4 oxidation state. So what you'll find is that carbon can go anywhere from +4 all the way to -4 and anything in between. Whole number, that is. All right? So that's how you calculate oxidation state. What else you got for me?
Does the SM1 mechanism, does it retain configuration of the stereocenter?
It does not.
It does not. Why doesn't it?
All right, so the SN1, so let's suppose we take a tertiary alkyl halide, and let's say it's something like this. So we got, let's say we got a hydrogen here, and we've got another group here, so let's put let's just put CD3, and this will be CH3, so it'll be simple, okay? Those are different groups. D is deuterium, okay? No, not hydrogen, excuse me. OH, we're doing SN1. So I need to change that to CD3. So let's say we've got that. And let's say that we react that with HBr. I know that the first step of the reaction is for the oxygen to get protonated. Right? That's the first step. And now I know that the bromide cannot come in from the backside and push out the OH2 because it's too crowded, right? It's a tertiary center. But the water can leave, and that gives me a carbocation that's planar. And I'm going to draw the waterway over here. Let's just assume it got completely out of the way. That's not entirely true, but let's just assume it did. Now what happens? The bromide attacks the carbocation to make an alkyl halide, right? That can happen from either the top or the bottom. What are the odds of it happening from the top or the bottom? 50-50. There's no reason to suspect that the top's any better or worse than the bottom. It's flat. So the bromide, if it just happens to be over here, will attack from that side. If it just happens to be over here, and there's no reason to expect it to be one place or the other, so it's 50-50. And so in fact, you generate this bromide as a racemic mixture. So you go from, let's just say that's the positive enantiomer, rotates plane polarized light in the positive direction. So you take something that's real expensive and you make something that's dirt cheap. That's going to get you fired. Right?
That's why it doesn't retain optical activity either.
It does not retain optical activity. Okay, now,
Makes sense.
I'm telling, if you want to take more organic, we can learn about partial, but we're not doing that in this class. You assume that the water got completely out of the way. That's why I said I'm going to draw it way over here. Right? That's not entirely a true statement, but it works 99% or 95% of the time. Okay. So that's why an SN1 reaction does not give you inversion of stereochemistry. SN2 gives us inversion of stereochemistry. Remember, SN2 reactions, you like primary alkyl halides or Secondary alkyl halides, so Rx. We'll do SN2. We know that the rate is equal to the concentration of the nucleophile times the concentration of the alkyl halide. We know that it goes with inversion, stereochemistry. So if it was R and it went through an SN2 reaction, I know that my product has to be S, right? I know that it has to be inverted. SN1 is completely different. SN1 works best on tertiary alkyl halides, or tertiary alcohols. It also works okay with secondary, but not quite as good. I know that the rate of the reaction is equal to some rate constant times the concentration of the alkyl halide, and that's it. It doesn't matter about the nucleophile, right? I know that the stereochemistry is going to be racemic. There are differences between SN1 and SN2. The SN2 reaction energy diagram looks like that. No intermediates, just a transition state. The SN1 reaction looks something like this. 2 transition states, 1 intermediate. That intermediate happens to be the carbocation. Right? So this is what the energy diagram looks like for SN2. This is what the energy diagram looks like for SN1. Good question.